Hi, I'm Rich Caruana, machine learning researcher at Microsoft Research here in Redmond, Seattle. And we've got an exciting session with 3 talks for you. The session is about saving lives with interpretable machine learning, using interpretable methods in machine learning in healthcare. And I'm going to give the first talk, and I'll basically be talking about how if you're using black box methods in machine learning for healthcare, that can put people at risk. And interpretable methods can help us understand what the model has learned, repair the model when it needs to be repaired, and even do things like learn from our data how we might be able to do better healthcare. Then after my presentation, Ankur Teredesai, who's from the University of Washington in Tacoma, and Ankur is also the creator of a company that's here in the Seattle area that does machine learning for healthcare. Ankur is going to talk about fairness in machine learning when it's used for healthcare. So how to prevent bias, detect bias, and those kinds of issues. And then the last talk is going to be by Marzyeh Ghassemi, who's a professor at the University of Toronto. Marzyeh is also one of the CFAR Canada chairs in Toronto. And Marzyeh is going to talk about explanation and AI and machine learning when it's used for healthcare, and that things aren't always as easy as you think, and that in some ways, explanation might actually be a little harmful, and in other ways it might be helpful. So she's going to give us a presentation on that. So anyway, let's get started with the session. We're going to have 3 recorded talks. Each will be about 20 minutes long, and then at the end we're going to have a 30-minute session for Q&A. So please stick around at the end. Come up with questions. You can type them in the chat window. Let us know what you'd like to talk about, and we're happy to discuss all of that at the end. Hey, thank you very much. Hope you enjoy the presentations. See you soon. I'm Rich Caruana, and I'm going to talk about using interpretable machine learning to save lives in healthcare. Before I start, I want to thank a number of people who have worked on this project with me over the years, in particular 4 great grad students, Yin Liu, Sarah Tan, Shuzhou Zhang, and Ben Langridge. A surprising number of people in machine learning believe that if you train a deep enough neural net on a large enough data set, and if it looks accurate on the test set, it's just safe to deploy the model. There are some settings where that is correct, but in critical settings like healthcare, this can be very, very risky. The fundamental problem is that machine learning thinks very differently than humans. On the left is a panda that a deep neural net has pretty high confidence in. We add a little bit of noise to it that the model thinks might be a nematode, and then we get this new image on the right, and now the deep neural net is very confident that this is a gibbon. I can't even see a difference in the image from the left to the right, and yet the model has completely changed its mind. More importantly, I don't think any of the 7 billion humans on the planet could see this difference either. Obviously, the deep neural net works very differently than humans do. This is an image that the model is pretty confident is a cheetah, is a robin, is a redshank, is a lesser panda. And I'm also pretty sure that none of the 7 billion humans on the planet would have classified any of those things with those categories. So again, the deep neural net obviously is thinking differently than we do. Finally, here's an image that the model is very confident is an electric guitar, or is a baseball, or a starfish, or a remote control. And the model is doing something really interesting. It's capturing the rhythm of electric guitar, the stripes of the baseball, some of the pattern in a starfish, and the buttons on the remote control. But it's also missing things that are obviously important, such that the remote control is a small device you might hold in your hand, or the starfish has legs, or the baseball is a round spherical object. Clearly, these machine learning models, while they could be very, very accurate, think very differently than humans do. The problem is that artificial intelligence really isn't artificial intelligence from another planet, but we want to use it here. And it's going to make errors that are very different from the kind of errors that humans would make. It's not going to make predictions the same way doctors would. So we need to be able to understand the machine learning model to prevent risky mistakes and possibly to discover new things that the model has learned from the data. Here's how I got involved in this. Back in the mid-90s, I was asked to train a neural net on a pneumonia risk problem. The goal was to distinguish low-risk patients who could be treated as outpatients from high-risk patients who definitely had to be admitted to the hospital. 10% of the pneumonia patients did die from their pneumonia. The neural net I trained was the most accurate model anyone could train on this data set. And the question was, is it safe to use it on real patients? I mean, it's a black box, this neural net. We decided no, and one of the reasons was that somebody else doing rule-based learning learned the rule that if you have a history of asthma, it lowers your chance of dying from pneumonia. That is, asthma looks like it's good for you, protective, if you've got pneumonia. Now, we asked the doctors about that because that didn't make any sense to us. And the doctors said, wow, asthmatics are higher risk from pneumonia, not lower risk. You have to fix the models. But it might be a real pattern in the data. And their explanation was that asthmatics notice the symptoms of pneumonia sooner, they get to healthcare faster, and then they receive very high quality treatment because they are actually considered to be at higher risk. And this rapid high quality treatment actually lowers their chance of death compared to the general population. We assume that if rule-based learning learned that asthma is good for you, the neural net probably did too. But that's not the only reason we were concerned about using the neural net on real patients. What else might the neural net have learned that's equally wrong, like that asthma is good for you, but we didn't have a rule-based system that learned these other patterns and warned us about other things that might be lurking in the neural net that were wrong. So we were afraid to use the black box neural net on real patients because we didn't know what other things might be in it. This is a fundamental problem in all data sets, not just machine learning data sets. The problem is confounding. Asthma is acting as a proxy for two very important features that we're missing: time to care and quality of care. And this problem is ubiquitous. Every data set you're using is missing important features that you just don't have access to. Even important features that won't be discovered until the future, for example, your genome is not in your data set yet, can cause confounding on the features that are currently in your data. So you can't escape this problem. One way around it would be to run randomized clinical trials on everything, but we're not going to do that for problems like asthma, where we already know how to provide good care. We're not sort of going to kill a few asthmatics or randomize their treatment just to train a better machine learning model. That's not ethical. So we have to learn to live with the data the way it is. Unfortunately, you might think we could just clean the data or detect these problems in the data, but that's actually much harder than detecting them in the machine learning model. So we're not going to go that route. And although I won't talk about it today, this kind of asthma bias that we're seeing in the models, it's very similar to race, gender, socioeconomic bias. So the problem is that the bias is in the training signals. It's not in the learning algorithm. And the learning algorithm is just learning from the data. And that's where the problems usually lay. One way around this would be to have a machine learning model that's as accurate as a neural net, but as interpretable as, say, rules or logistic regression. You may have seen a graph like this, which suggests that there's a trade-off between accuracy and intelligibility. Very accurate models like boosted trees and random forests and neural nets are not very intelligible, and more intelligible models like linear regression, unfortunately, are not as accurate as we would like on complex data. So we're looking for a model in the upper right-hand corner here that is both very intelligible and very accurate. The good news is that for tabular data, we actually have an algorithm now sitting here, and it's generalized additive models with pairwise interactions. So that's what we're going to talk about today. Let me just show you briefly what that is. Here's linear models. This is a weight times a feature plus another weight times another feature. That's a linear model. Here's a full complexity model, just an arbitrary function of all the available features. Fortunately, there is something in between, and that's what's known as additive models, GAMs. Here's a function of the first feature plus another function of another feature plus another function of another feature. We have functions of features that are more complex than just multiplying by a weight. They can be arbitrarily complex. They can be multimodal and nonlinear, but they're still only functions of a single feature. And that greatly restricts what this model class can learn and also makes it intelligible. We can make that a little more complex. This is the sum of all functions of individual features, or we can add pairwise interactions, sum of functions of pairs of features, or all the way to three-way interactions and higher, functions of three-way combinations of features and more. We're going to restrict ourselves, though, to main effects, functions of single features, and a small number of carefully selected functions of pairs of features. And we're going to restrict ourselves to that because this remains intelligible, and then our goal is to get maximum accuracy out of it. Now, we didn't invent GAMs. They were invented by Stanford statisticians in the late 80s. But they were very conservative when they fit the models, and they didn't have the kind of horsepower in modern machine learning methods that we have now. So they didn't get as much accuracy and intelligibility out of these things as we're able to do now. Our contribution is that we're going to put these things on modern machine learning steroids, and in the process, we're going to get higher accuracy, much higher accuracy. We're going to get improved intelligibility, and we're also going to get editability, and that's a great combination of features. This is the pneumonia data set collected in 1989 that motivated all of this work. So we have a number of features like age, gender, if the patient has cancer or asthma. Patient has a physical exam, we know their temperature, what their breathing sounds like, what their heart rate is. There's been a blood test, so we have the lab findings from the blood test for the patient. And then all these patients have had a radiologist read a chest x-ray, so we have notes from the chest x-ray. Now the model class is a function of a feature plus a function of a feature. There's 46 features, so we're going to have 46 functions. And then we'll throw in 10 pairwise interactions as well, although I won't talk about those today. So in the end, we'll have 56 functions. Here's what it looks like from a high level. We're going to have a function of age represented as a graph, a function of asthma, a function of your respiration rate, a function of your blood urea nitrogen. And the way you use these 56 functions is you read the patient's age on the x-axis, write down the y value, so it might be minus 0.23, and that's what this particular function predicts. Then we go on to asthma. We write down if the patient does or does not have asthma, write down a number. We're going to get 56 numbers like this. You add them all together. The more positive the score, the higher the risk. The more negative the score, the lower the risk. These are basically log odds. So we use the logistic function that's used in logistic regression all the time to convert this score into a probability. In this case, a probability of dying from pneumonia. It's just 1 over 1 plus e to the minus score. So if a patient had a sum of scores that was equal to minus 0.78, then their probability of death would actually be very high. It would be about 30% chance of dying. So you want to be a -2, a -3, or a -4 on this scale. This is what the model learns about age. So I've just zoomed into one of the 56 graphs. So the bottom is a histogram of the distribution of our patients. Most patients are between 60 and 90, some patients younger than 50, 20s, 30s, and 40s, and a few patients at around 100. The top is the risk model that's been learned by the generalized additive model. And it's learned this in parallel with the other 55 graphs. That is, it's learning all of these things at the same time. This is not marginalization, if you're familiar with that. So let's read the graph. Remember, down is low risk, high is higher risk. It's good to be young, and the model is saying that young is anything under, say, 50 years old. So and it doesn't distinguish between people in their 20s, 30s, and 40s. It just sees them all as being equally low risk. Risk goes up slowly as you go through your 50s into your 60s. Rises pretty rapidly around 66, 67, 68, 69. That's retirement. Then it continues to rise rapidly as you go through your 70s into your 80s. There's a surprising step function rise in risk right at 85. Then a surprising flatness in risk in the upper 80s and 90s. And most surprising of all is a drop in risk that's happening right around 100 and 101. So let's talk about that. We're pretty sure this rise in risk is due to retirement. You might have thought retirement is good for you, but in many medical data sets, we see that when patients retire, their risk actually goes up a little. So this is consistent with other findings. This rise at 85 is surprising. 85 is a very round number, and we're pretty sure what's happening here is that doctors are giving a little less aggressive care to patients who are over 85 as opposed to patients who are under 85. This data set's from 1989. It's a very old data set. And back then, patients who were over 85 were definitely considered to be on the elderly side of being elderly. And pneumonia was even sometimes called the old man's best friend. The idea being that you have the illnesses associated with being this elderly. Because of those illnesses, you've gotten pneumonia. And now, within a week, it's possible that the pneumonia is what takes you out. And perhaps that's a friendlier way of passing than it would be to have a sort of longer wasting illness associated with the other comorbidities associated with being so elderly. The flatness in risk might be due to what's known as successful agers, people who have good genes, and if they've made it into their 90s, perhaps they're really at no higher risk from pneumonia at age 95 than 90, but we're not sure if that's an explanation for this flatness or not. The drop at 100, though, is really surprising. So why would risk go down right at 100? It's likely not a biological effect. It's probably a social effect, just like this rise in risk at 85. What doctors tell us is when they've got a patient over 100 who has a treatable illness such as pneumonia, they just don't want to give up on this patient. Like they just keep fighting. If the patient needs a second or third round of antibiotics, they go for it. And they'll do anything they can to keep that patient alive because the patient has made it to being 100. They're a centenarian. And that's a really remarkable thing, especially back in 1989. So we're pretty sure that this is a social effect here where doctors Just don't give up on very elderly patients who have made it to 100. Now, an interesting thing about this model, we've been talking about detail that's on just one of the 56 graphs that form this model. I'll show you 2 other graphs. This model, despite all this detail we're able to see in the graphs, is actually just as accurate as the neural net. In fact, it's slightly more accurate. This is the most accurate model we know how to train on this data. So that's kind of remarkable that we can get all of this intelligibility about the model, really understand how it's making its predictions and what it's learned from the data, and we've been able to do that without any loss in accuracy. So that's great. Now a question. How many people actually think that we should predict that a patient who's 105 is lower risk than a patient who's 95? I mean, does that make sense biologically? Probably not. We think this is because of the extra care the centenarians are getting. So we can fix that if we want by enforcing monotonicity in the model. The model is a series of graphs, so we can edit those graphs. And if we edit the graph this way, then risk will slowly go up for all patients above 85. And the model will just do what we say. Now, an interesting question, would you always want to edit that graph? Well, it turns out if you're an actuary whose goal is to predict just which patients are going to live or die, you don't actually plan to intervene in their healthcare in any way, then you're probably happy with the original model because it's telling you something about the survivability of patients that you're ultimately responsible for paying for their healthcare. So you might want to keep the model the way it is and just benefit from the fact that you've learned now that patients over 100 are actually a little more likely to survive than patients in their 90s. Or maybe you're even happy to use a black box model like a neural net and you just want predictions, though there probably is an advantage to learning this from your data. That's very important. So model correctness and whether it's safe to deploy the model depends completely on how the model is going to be used. The original model is good for health insurance providers, but not if we're going to use it to decide what treatment to give patients. So that's very, very, very important. Let me show you a few things this model learned. First of all, jumps that we see in round numbers or numbers that are very meaningful, like age 18 and 21 in the US, are almost always due to human social policy effects. They're not phase changes that are happening in the biology or physics of the world. The model learns that asthma is good for you. So the asthmatics are on the right here, and notice that the graph goes down. Remember, that's how this whole problem started for me. So the model learns this, and we can fix this now by just editing the graph to make the effect just be completely flat. That is, we can remove the asthma effect by making the graph go straight across. Or a doctor might say, no, I want the asthmatics to be higher risk. I want the graph to go to plus 0.5 for the asthmatics. And if they tell us to do that edit, we can do that. And then the model will now predict that asthmatics are higher risk, not lower risk. But there are things that the model has learned from the data that are actually more surprising than that asthma is good for you. It learned that a history of chest pain and a history of heart disease are both good for you. So the heart disease patients are over on the right, and that's even better than having asthma. And we think the explanation is exactly like the asthma explanation. Patients who have a history of chest pain and heart disease are afraid when they start getting pneumonia that those symptoms mean they're actually having a heart attack. And because of that, they get to healthcare very, very fast, usually going in through the ER, whereas the asthmatics don't usually go in through the ER. So these patients get to healthcare very, very fast, and then they get high quality care when it's determined that they're not having a heart attack, but that they have pneumonia. So that means that their risk is even lower than, say, the asthmatics. But there's something even better than heart disease and asthma, and that's a kind of wheezing called stridor that doctors are trained to recognize that indicates one of your airways is actually obstructed. And the reason why this is good for you is because patients could ignore that their asthma seems worse or that they might have symptoms that might feel like heart disease. But you can't really ignore the wheezing that comes with stridor. I mean, it is so loud and obvious that if they were in a meeting with other people, the other people in the meeting would tell them to leave and right away go to the hospital. That's how bad stridor is. You can't ignore it. And the good news is, even though your pneumonia is fairly progressed for you to have stridor, the symptom is so strong, this forces you to go to healthcare and get treatment. And if you get treatment early enough, that's always good for you. Now, here's an interesting thing. The model is additive. So it predicts that a patient who's 105, who has a history of asthma, heart disease, recurring chest pain, and now has stridor, is actually one of the lowest risk patients. Moreover, it's rewarded with extra high accuracy on the test set for predicting those things, and that's because the test set looks just like the training set. It's just a random draw from the training set. So the model is being rewarded for making predictions that are terribly wrong. So we have to be able to see these things in the model and fix them. You can't trust accuracy to tell you whether the model is good or not, because it'll actually be rewarded for doing unusual things like this by the test set. So it's good we didn't deploy the neural net back in the mid-90s, because it probably had learned these very same things in its 10 million weights. But with this kind of model, it's like having magic glasses. We can see these effects in a really accurate model, and then we can repair the effects if an expert like a doctor tells us that we should. By the way, you might have thought we could fix this problem by removing, say, the input variable for heart disease from the model. How can it predict your lower risk if you have heart disease if it doesn't know you have heart disease? And that doesn't work usually. What happens is the bias is coming in the training signals. The fact that the heart disease patients really do die less often is in the training signals, not in the input features. Input features aren't usually biased. So what happens if you remove that input feature is, because of correlation with all the other features that you have to keep in the model, it'll still do its best to learn to predict that heart disease patients and asthmatics are lower risk. So what we do instead is we make sure features like this that we're worried about stay in the model. We let the model learn the worst thing it can on those features, and then we can detect the problems that are in our data, and then we can correct the model by editing the graphs. Now, intelligibility doesn't only help us detect problems with our model, it can help us create new science, learn from our data. This is a graph of risk as a function of blood urea nitrogen, a blood test all of us have had. And doctors really liked this graph because they could see the impact of their treatments in the graph. Notice that risk goes up starting at about 35 and levels off right at 50. And then risk continues going up if your BUN is higher, and then levels off and actually drops right at 100. And those are treatment effects. So the doctors start to treat high BUN with a medication at about 50, and you can see that medication is effective because risk flattens off. And then at 100, they start to do dialysis on patients, and that's so effective that all the patients, say at 110 or 115 who are getting dialysis, are actually a little lower risk than the patients who are at 90, who are healthier patients to begin with. So the doctors were thrilled that they could see these treatment effects in the graph. But they were concerned because they noticed risk is very high by 35, and they wondered if they shouldn't change this treatment threshold from 50, maybe down to 35 or 40. And this made them even more concerned. The fact that patients who are less healthy with a BUN of 115 are lower risk than patients at 90 who are healthier really didn't sound like a good treatment strategy to them. And they thought maybe they should move this treatment threshold for dialysis from 100 down to, say, 90. Because it's an additive model, we can treat it almost like a spreadsheet and do a what-if analysis. We can conservatively estimate that if we were to move the treatment threshold, say, down to 85, that patients would look like this red line or perhaps below the red line, that would be the actual risk profile. And the area between this red line and the original green graph, those are people dying. So that's probability of death that the model's predicting. So we can estimate that by making this one change to this one treatment threshold on this one graph for one illness, for pneumonia, that we can save as many as 2,500 lives per year in the United States. So that's really remarkable to be able to see that from your graph. Now, treatment effects abound in all data. This is systolic blood pressure. Notice there's an effect at 150, there's an effect at 175, 200, 225. We see this sort of thing all over the place in data. And you really want to be able to see these things to determine if you need to fix them or not. Now, let me show you something more recent. So we've been working on COVID-19, which is an illness that doctors don't even know about. So now we can use what we learned from data for COVID-19 patients to help tell doctors how the disease works. Notice that the highest risk factor is kidney disease, which has been widely reported in the literature. We won't talk about chronic bronchitis and Parkinson's because we have very few patients with those conditions. But we have a lot more diabetics and hypertensive patients in the data, and notice that those are also significant risk factors. And then there's something very surprising, which is that asthma, or people with pulmonary disease, active cancer, or coronary heart disease, these all seem like pretty low-risk patients. And other groups that are studying COVID-19 are finding this. And we don't know whether the explanation is like asthma and pneumonia, that these patients are just getting better health care more rapidly, or whether, in fact, there might be something protective about asthma and COPD, for example, for COVID-19 patients. So that's something we're actively looking at. Let me wrap up. We definitely want to use machine learning to save lives in healthcare. But high accuracy on a test set does not tell us enough for us to safely use a model in something mission critical like healthcare. So these treatment effects are all over the place in healthcare because the patients are all receiving treatment already for their conditions, and that affects the data that you collect. And these models are rewarded with extra high accuracy on test data for doing stupid and risky things. So you need to be able to see what the models are trying to do. And this sort of retrospective test set analysis, realize it's always optimistic. Ultimately, you need to be able to do a prospective analysis. But before you do that, to be safe to patients, you want to see the model and edit it if necessary. The bottom line is the data is always wrong in surprising ways that you really can't anticipate. And intelligibility is your way of getting past that obstacle. These intelligible generalized additive models with pairwise accuracy really do give us accuracy, intelligibility, and editability comparable to any other model on tabular data. And we open sourced a package for training these models a year ago. So we encourage you, if you're already using random forest, boosted trees, simple neural nets, or logistic regression, we think you would be better off actually using these generalized additive models. The bottom line is machine learning really is a foreign intelligence. It's an alien. It learns and makes mistakes differently than humans. And intelligibility is the main trick that we know how to use to help correct this alien intelligence when it does things that would be risky in healthcare so that we can safely deploy hospitals and save patients' lives. Thank you very much.
Thank you, Rich, for the invitation and Microsoft Frontiers in ML conference for this opportunity to participate and present my work. Fairness in healthcare is a complex topic, and it's a major topic in making the use of AI more responsible and accountable in healthcare. Today, while the topic may be complex and very much in the limelight, we will focus on a few key issues which are in the news due to recent events. And I wish to share the components of a working solution framework for unbiased healthcare AI. And I'm hoping to both educate and inspire you on the key issues in this field. But first, let's get a working definition of healthcare in our minds. We often think of healthcare as care needed when the human body goes crazy. Many of us think of it like fixing the engine or the transmission when a car is broken. We often don't think of healthcare being on a spectrum, from early detection to proactive interventions. The term wellness often reflects the goal of AI-driven decision making across the care continuum. This is one view of that future of healthcare AI. The x-axis is time, and y-axis is the degree of automation, or as I like to call it, assistive intelligence. Today, we live in a world of rule-based systems, shown in gray, and increasingly, we are in the coming decade, we are already starting to see use of AI and machine learning for diagnostic decision support tools. I bet in another 2 decades or even sooner, we will see increasing automation for AI-driven ventilators, AI-driven insulin pumps, and we will be, and each of these will be probably clinically approved. The era of proactive intervention will subsume the inefficiencies of a reactive guidance that machine learning is able to provide today. Over the last decade, I have worked closely with numerous health systems across the world and realized that every stage of the continuum of care, from birth to death and everything in between, has a corresponding objective function in AI. In fact, every prediction problem in healthcare has multiple objective functions depending on who the user or the end consumer of that model output is. A clinician prescribing labs, a nurse practitioner raising an alarm of code blue, or a social worker helping a diabetic patient get screened regularly to patients or to patients themselves who may be nudged differently by their Fitbits and Apple Watches. depending on when they last went for a run. AI will integrate and interfere with the practice of medicine. So we must now be very careful on how we create solutions for healthcare using machine learning. And one of the things that we have to be very careful about is what Dr. Martin Luther King Jr. was highlighting 54 years ago. He said, to quote, "Of all the forms of inequality, injustice in health is the most shocking and most inhuman because it often results in physical harm." I want to reiterate this as the inspiration for us to discuss fairness in healthcare AI. Imagine an emergency room on a Monday morning at a large US city downtown. Amongst other patients with severe wounds and trauma waiting to be seen by a physician, there are three patients with mild chest pain also waiting in that emergency department. Now imagine the triage nurse is using your AI model to help her bring to attention the most severe of these three patients. It has been shown in numerous studies, that rule-based systems that don't use any machine learning or AI often have a very low precision that hampers the decision-making prowess of the entire emergency department. So now this hospital is using a more precise machine learning driven algorithm to streamline the flow and improve patient outcomes. After using the system, imagine that after using the system for a few months, there seems to be a problem. The model always fails to correctly restratify the uh, accuracy or the severity of illness of a specific race and gender when trying to select who to prioritize based on chest pain symptoms. This is in spite of us having recent data on which the model was trained. Folks, this scenario is not imaginary. The city is Chicago, and the model was something that we trained and was later revised when we realized that the chest pain factors that we were using were from prior studies that did not include any black males. Bias, discrimination, and unfair practices in healthcare are not hypothetical. In fact, policymakers across the world are also becoming increasingly aware of this issue of AI adoption, roadblocks, and see algorithmic accountability as a very important factor. While we know that GDPR and the European Union regulation has been ahead of the curve, even the US Congress has been trying to pass Algorithmic Accountability Act, which would make FTC require accountability from algorithmic systems. The relationship of this with HIPAA and other laws that address patient privacy remains to be seen. There are racial and bias statements against African Americans, blacks, and many other races and genders, uh, pretty much all across ancient history, from medical literature, be it in Greek, Indian, or Arab or Chinese medicine. The roots of modern bias and discrimination in healthcare go all the way back to the birth of modern science. Representation of blacks in the medical profession was non-existent in the West, which made the perpetuation of such bias even more easier or worse. Healthcare, in fact, is rife with inequality and racial prejudice. Three examples of these are presented here. The Tuskegee study was deplorable. Sickle cell was underestimated or understudied for a long time, and human-led bias led to discriminatory selection of candidates for clinical trials for bypass surgery for a very long time. These are but few examples of issues machine learning and AI will have to think about broadly and address them when we talk about fairness in healthcare ML. The main point I'm driving towards, as you can tell by now, is that this is not just a data bias issue. Designing techniques that address issues in data are not going to be enough to address fair and trustworthy AI systems in healthcare. And it's obviously not just a race issue. Gender discrimination has also played a major role in delivery of healthcare. According to a 2009 analysis of US healthcare, US women make up for just 37% of the research subjects, even though they comprise of more than half of the US population. To stress the point home, medicine is not alone in this. In fact, computer science and our own community has also played a key role in algorithmic discrimination all the way back to the 1970s. The literature on fairness and bias in machine learning started to appear in the late 1990s and early 2000s. It was not until 2010 that it became a prominent subject of the AI ML community, and recent articles are starting to shine the light on this issue. So, the role of all of us in this community will go a long way in shaping the solutions. But is it just a data problem? I don't think that generalizability and representativeness of AI models are a data problem alone. EHRs or electronic health records are notorious for observational biases. The data doesn't just reflect the health of the patient, but rather it reflects the interactions of the patient with the healthcare system. Example would be the detection of diabetes in an electronic health record would only happen when the physician made the diagnosis, not when the patient actually developed diabetes. We also know that electronic medical record systems are primarily used for billing, and there are many other such issues with data in the healthcare system. But data is just a signal, and we have to treat that signal appropriately. Fairness in machine learning is more than imbalanced data sets. In fact, Google Cloud study in 2018 talked about an entire pipeline of data sets from issues in collecting and gathering and pre-processing the data, from imputation to building the models to running the training and evaluation of these models, and ensuring that all the models are treating all the protected attributes fairly, and then how to set appropriate prediction thresholds when we deploy the model in pipelines, and how to understand the model behavior post deployment in order to make predictions, and then address the issues as we talk about ensuring deployment fairness compared to training fairness. This is my own distillation of the dimension of fairness in healthcare AI. And I have collaboratively worked with several researchers from both Kensai and University of Washington, as well as a global research team of healthcare partners in various healthcare organizations to think about how we break down fairness in healthcare AI. The social, cognitive, and computational aspects of AI or models have to be taken together in order to determine fairness in machine learning. Here is a overarching framework of how we need to start thinking about sources of bias in healthcare AI. We are very focused on the data bias issues, but we also need to look at the non-data bias issues such as model bias, the loss function bias, the post hoc optimization biases. In fact, I would cross over to discuss one more issue of bias in delivery and bring in the idea of handling cognitive biases and social biases as machine learning systems help improve patient outcomes. Under that definition of different biases, uh, the solution framework I'm proposing includes a articulation of the sources of such bias, all the way from selection and sampling bias to understanding lack of explainability, and assuming that the models are fair. And there are various ways to mitigate that bias. Of course, equal representation and ensuring that the data quality is better is just one way, but it's certainly not the only way. It is not even sufficient to just do that. Bias mitigation algorithms have to be designed, appropriate fairness metrics have to be discussed, and explainable AI has to take a huge leap ahead in order for the entire system to become unbiased. It is also important to acknowledge the quality of social context in the explanation of the explanations produced by the machine learning model when we talk about delivery of the predictive insights in healthcare settings. So, uh, clinicians, practitioners, and designers of user experiences, as well as the entire delivery team that handles a particular AI rollout in healthcare, starts becoming extremely critical when we discuss fairness in machine learning in healthcare. So fixing the computational bias, that is data and model bias, may not be enough. There are certain aspects uh, of thinking around the definitions of fairness that have been proposed in supervised machine learning, and they fall into six major sort of categories: unawareness, demographic parity, equalized odds. These three can be grouped into a group fairness aspect. And then the predictive rate parity, individual fairness, and counterfactual fairness all deal with the underlying features and how these features play a role at the individual level as well as the predictive model level. An important issue, uh, and I'm going to highlight this through examples of our own work on why artificial intelligence or AI needs fairness, accountability, and transparency. The data in this plot tells us that children and young adults of different ethnicities are bound to have different distributions of HbA1c values just within the United States. HbA1c is an indicator of diabetes, and any model that ignores this variation will optimize for the ethnicity that is most prevalent in the underlying dataset on which it was trained. Not just ethnicity, but age, gender, and even social determinants of health uh, can, can significantly vary the output of the AI model if it is not tuned to estimate and eliminate such bias in the production system. Let's look at one problem that we do need to solve for healthcare very actively and every day. It's the problem of predicting length of stay of a patient in the hospital. This prediction of length of stay helps with proper discharge planning, it helps with bed turnover, it helps with just managing the patient flow. And particularly in these times of COVID-19, predicting length of stay of patients is quite useful in understanding the load on the system. The blue bars here are longer stay patients, and the gray bars are the shorter stays. Obviously, the number of short stays in the hospital is much higher than the number of longer stays. If we study the distribution of longer and shorter stays across different protected attributes, we should start seeing if the eventual model that predicts length of stay will be fair or not. On this plot, we observe that across age groups, the short and long stays seem to be distributed appropriately. In fact, when we look at gender categories, the distribution also seems to be equitable or reasonable compared to the long and short stays. Yet, when we look at race as a factor, we start seeing that there is significant race category disparity between longer and shorter stays, leading us to believe that uh, accommodating or creating customizations and adjustments for evaluating fairness in the length of stay prediction is extremely important across these categories. This type of an implementation actually led to significant improvement in the accuracy and adoption of the length of stay model at a large Midwest US health system when we put these mitigations in place. Here again, we see the impact of that fairness across the machine learning pipeline. This is joint work with students at the University of Washington and collaborators at Kensai. And there are dozens of such definitions of fairness, but they can be mapped into six main categories. We will look at a few of these in the next slide. Uh, the definitions as well as the formulations of each of these categories is given on the screen. I won't go into the details of each of these here, but suffice it to say that none of this is complete or conclusive. There are many flaws with each of these definitions as well, and we can discuss this at the panel. In fact, I was surprised in my research to find the impossibility theorem of fairness. It actually says that three different types of fairness formulations: demographic parity, predictive rate parity, and equalized odds can actually be mutually exclusive theoretically, such that we cannot optimize for all three or minimize or maximize all three at the same time, and thus leaving us in a conundrum on how to fix fairness. Greater than that, the fairness versus accuracy trade-off is well known, and we must tread carefully, being aware that making the ML model and the pipeline fair will not always result in the best possible accuracy, even post-deployment, but we may have to make some judicious calls. And that is what makes this topic so complex. So how then do we make ML models more fair? First, let's ensure that incomplete or underrepresented values in the data are known and communicated to the appropriate end users. Second, let's design algorithms that are bias-free by choosing the features carefully that are consistent with the interpretability expectations of the end user. And third, and equally important, is to compare the performance between different AI systems and select the consistent performance, not just against accuracy or precision recall as a metric, but rather the many measures of fairness that we have designed or we are designing now for choosing the best performance. Let's revisit this framework once again of understanding the types and complexities of fairness that we may have to deal with, along with the mathematical formulations and the implications of each of these. And we also need to be aware of the flaws of each of these fairness metrics in order to then make sure that our healthcare AI systems are accurate and fair to the best possible extent. I do have uh, an ask for call to action to partner with us. It takes a village. So I hope all of you inspired by this talk will contribute in some way to deploy grade AI and ML models in healthcare across the globe, and will consider fairness as an important aspect. There are many websites that talk about fairness in AI as an issue. In fact, there are very nice libraries that are coming out from different contributors that talk about uh, fairness in AI. Some of these need to be used in healthcare, and we are working tirelessly to release our own. And last but not the least, in a month from now at KDD, uh, I and Muhammad, Dr. Arpit Patel from University of Washington, Dr. Carly Eckert, and Vikas Kumar are doing a KDD tutorial on exactly this topic of fairness in machine learning for healthcare. I hope all of you will join us there as well for a deeper look at this topic. With that, I want to thank you for listening, and we'll take your questions on the panel.
Hi, everyone. I am Marzyeh Ghassemi, and I'm going to talk to you today about explaining yourself, or why I think there is false hope in promising explainable machine learning in healthcare. And the reason that I became interested in machine learning in healthcare initially is because algorithms are really a huge part of healthcare already. We already use risk scores, calibrated models, and these have been used for decades to try to understand patient risk or who needs a specific intervention. But now these models have become not just certain risk scores for high intensity situations, but we're seeing across a range of human conditions, state-of-the-art performance. And so for each of these lines, you see a model was created that did as well as or better than a human equivalent. And so this has changed the conversation recently from one of these are tasks where we need some sort of calculation or risk score to help us with a decision making to perhaps here we actually have models that can perform better than a human can. So my research focuses on creating these actionable insights in human health. I focus mostly on what models are healthy, so trying to optimize models to do well in particular health settings and on health data. What kind of healthcare is healthy, using those to investigate how we make models private, robust, and fair. And finally, what kind of behaviors are healthy, understanding how we can best deploy these kinds of models in the field, even if they are robust, private, and fair, and well optimized. So one thing that has come up repeatedly across all of these areas is the idea of transparency, of explainability. And the reason that I think that transparency is a big phrase right now in machine learning for health is that interdisciplinary mismatch creates this difference in expectations because we have difference in expertise. There are many ways of asking for transparency for a model, but I'll focus mostly on explainability. There has been some very good work done in the robotics community on when humans trust, overtrust, and undertrust robotic systems that are meant to assist them. And specifically, humans tend to overtrust robotic systems in scenarios where they believe that a robot can perform a function they cannot, or when they believe a system can mitigate risks on its own. So this is true in healthcare, for example, when we have an MRI machine that can take images that you can't, or when you have a bed assignment algorithm that you think will mitigate risks about patient severity of illness. There's been some more research specifically on the health side about generation of images. And so radiology images, or X-rays, are often used in triage. And so some researchers have tried generating these images as part of explanations or recommendation systems. But what they've found is that humans, these are radiologists, actually sometimes prefer fake images to the real images. And so here you can see that if these images, which are very high quality, were just as good as the real images, and people tended to preference them just as often as the real images, you would see most people at a rate of 50% for users choosing GANs as the real images. But here you see there's large variation in human preference. And this kind of variation really leads to the crux of the issue with healthcare. Healthcare and health are about human decision-making, a collaboration between a patient and a provider and a community. So if ultimately our goal is improved care, we need to ask some questions. How does advice impact expert or non-expert clinical decisions? What role does accuracy of that advice play? And is advice rated or thought of differently if you think it's from some sort of algorithm, model, or AI? And so we designed an experiment in the X-ray domain to test this. So we have X-ray images, and we gave them to clinicians, both experts and non-experts. So we gave them these X-ray images. We gave them some advice. It was accurate or inaccurate. And we told them it was generated by either an AI or by a human expert. And then we asked them, can you give us a final diagnosis? And then can you rate the quality of advice that we're giving you? And what we found is that task experts, radiologists, rated the AI advice lower than human advice, and the error rate is the same. We're giving them the same correct or incorrect advice, so there's no difference in the quality that we're giving them. But when they knew that the advice was from an AI, then they rated it significantly lower, as shown here. But this was not true for the IM/EM doctors. And this was true even after correcting for age of the clinicians. So it's not just how old you are, how senior you are. It's actually your level of expertise, what you believe your level of expertise to be. That seems to be interacting here with the advice. And then even though people with more expertise are rating this advice to be lower when they think it's from an AI, they still fail to dismiss it just as often. And so the accuracy that radiologists have under both advice types is similar. It's not statistically significantly different. So there's a level of mistrust of AI advice in the quality rating. But what the clinicians are saying, what these expert clinicians are saying, is not reflected in their actions for how they're using or dismissing the advice. We further looked at susceptibility. If you pick an accuracy level, 80%, you could assume that anybody who does this well is doing reasonably well on the cases that we've given them, right? And if we draw this dotted line, you can see more of the expert doctors, more radiologists meet this bar of getting most of their patients right. And fewer of the less experienced doctors, the IM/EM doctors, get this right? So you can see that by who is above or below this yellow dotted line. However, if you look at susceptibility, which we defined as getting every case where you were given inaccurate advice incorrect, we have a similar number of expert and non-expert doctors who are susceptible to incorrect advice. And this is not significantly different whether we give them AI advice or human advice. It's not really that it's AI that's giving you an advice. It's that incorrect advice itself is sometimes challenging to dismiss. Explainability, I believe, is not a panacea. There's been some recent work on the interplay between machine learning and human decision-making. The specific situation this was tested in was in the New York housing market, where they said, look at this unit. It has a certain number of bedrooms and bathrooms, and tell us whether this model estimation of a rental price is a reasonable estimation. And what they did was occasionally they put in an example of a unit that had a very poor configuration. It had very many bathrooms and one bedroom. Models that were more transparent, where there seemed to be a formula that was listed for how the model got its recommendation of a rental price, these more transparent models actually hampered people's ability to detect when there was a serious mistake. This was not true with the black box models. People were able to see that the model had made an incorrect or overestimate for the rental price. And so models that are more transparent can sometimes make people feel like a choice is good. They're making a good choice. They're confident in their choice. They're not going to do a more aggressive audit because this model is just confirming a bias that they might have had or an anchor that they might have had. Now, with this example, I want to recognize that there are some very good reasons that you might want this in human healthcare decision-making, even if you don't have it for rental prices. Because we believe that decisions about routine practice should be justified by evidence or in evidence. But the issue here is that many of the practices that are used or have been used in the past 10 years are contradicted by studies that get published in top journals. So these are things like Lancet, the New England Journal, or JAMA. And it's not a small number. It's over 10% in the past 10 years. And we don't audit doctors for their accuracy or for their performance. Doctors are a self-governing, self-regulating body. There's no federal entity that checks to make sure that you have a specific cure rate or that you treat all patients equally. You have to have a panel of your colleagues evaluate you. And this is a very difficult question that we're asking panels of people to do. And finally, individual doctors have been shown to have strong preferences about the kinds of patients they treat and the kinds of treatments they use. And so there's a lot of variation here. This is very similar to these other situations in robotics or in rent estimation that have been studied because there is so much variation. So arguments for explainable models do exist, and they're good arguments. So things like principle. There's a principle that I have a regulatory standard where I want an amount of information to be available to any person. So a good example of this is GDPR, which states that meaningful information about the logic of an algorithmic decision is a right of every person. There's other arguments. Maybe it's not a regulatory standard, but it's necessary in high risk situations. So when experts are using models, they need explainable models. And finally, there's a very good argument that it's important for fairness because these black box models that we don't understand could create, increase, or propagate biases. I think the first argument is a reasonable one. It requires significantly more technical detail about how it could be achievable. For whether it's necessary in high-risk situations, I'm going to focus specifically on clinicians because this is about healthcare. I think it's only really important that we have transparency when clinical opinion differs significantly from a prediction. That doesn't mean that all clinicians will care about exactly how a model works or that simple models are necessary for the sake of transparency. As we've seen, simple models are not a final solution. What it could mean is that clinicians need to understand when they should rely on or reject model outputs, that they need a notification of what populations a model might work best on or fail on, or that there should be limitations of data models that are trained. So technical options that exist currently are transparency via these post hoc explanations. And these could be useful if they are consistent, which means different model behaviors give you different explanations, and similar model behaviors give you the same explanation. So things like attention-based explanations or saliency maps are very common in images, but these are not always consistent. There have been some fixes proposed recently for doing competition-based explanations post hoc, which means that computing maps for all possible labels. And if you're in an image, competition over all pixels is used. But again, this is an ongoing field where many papers are published demonstrating that simple attention-based or saliency-based post hoc explanations are not consistent and they are not robust. So some of the work that we have done in explanations post hoc for clinical data is when predicting interventions in intensive care units. So if we look at patient data from the ICU, we could have static data, gender, age, other information. We could have time-varying vitals and labs, oxygen saturation, lactate level. And we could have all the clinical notes for a patient stay. If you put that into a matrix, there's many ways that you could learn what's going on with the patient and how to predict upcoming interventions. If we focus on these more black box style models, so recurrent neural networks or convolutional neural networks, you can ask for post hoc explanations. You can do feature level occlusions to identify which features are important for classes of predictions. So here we see that the physiological data is most important in invasive interventions like ventilation, and that these topics that we've learned across notes are more important for less invasive ventilation like a fluid bolus. You can also use convolutional filters to ask for maximally activating short-term trajectories for different kinds of intervention onsets. And so these are some ways that you can ask for post hoc explanations. Another option is transparency through natural outputs. What this means is that if transparency is just a way of calibrating a clinician's trust in a model, you could have clinicians and machine learning experts pre-training agree on a set of metrics that are a consumable end product, not just an intermediate risk score. And then you could deliver those metrics, and that would give enough explanation or transparency. So for example, if we wanted to create an end product like a report from a clinical image, we could automatically generate radiology reports given a chest x-ray. So this is challenging because unlike in image subcaptioning, where you want to comment on exactly what is in the image, like black and white dog jumps over the bar, you do not want to just comment on what's present in an image for a radiology report. You have to say, for example, in this image, there is no focal consolidation, effusion, or pneumothorax. In the impression, you have to say no pneumonia or pulmonary vascular congestion. So you have to first understand what topics could be commented on in the image and then explicitly confirm or deny them. And so here what we did is decided to first predict the topics that would be relevant in the report and then conditionally generate sentences that corresponded to the topics. We used a CNN, RNN, RNN architecture, which gives the model the ability to use these largely templated sentences, but still generate diverse text. And we also made sure to enforce a clinical coherence score in the generated text, because you don't just want human readable text, you want text that's actually clinically correct across a range of different labels. So we made sure that the generated report disease states were correlated and coherent with the ground truth report disease states. And by doing these, we had state-of-the-art performance in both readability metrics like CIDR, Rouge, and Blue scores, and in the clinical accuracy of the reports that we generated. And so if you take an unseen image, we evaluate our generated text and also compare it to the actual text. And the important thing here, I think, is that it's not just these readability metrics, which often reports are scored on. We have these natural language metrics that we are evaluating on, but we're also looking at disease accuracy. And ours is doing significantly better in this way. And so by giving people an end product that they want to consume, they would be able to say, is this readable and is it correct? Rather than just saying, is this score something that they can then use? The final option, if you don't want to do a post hoc explanation or a consumable end product that an expert can look at, is transparency in the audit of the embodied data. So all data is valuable, but particularly health data comes from human bodies, so it's embodied data. And we may want to focus more on aggressive audits ultimately, or even in addition to the other two options. And so we have new tools that have been proposed to understand both data and processes. So these are things like data sheets for data sets or model cards for model accuracy. And they help you understand the process and potential data biases and model biases, not just one individual output from a model. And so they're really valuable tools in this way. The last thing that I want to talk about briefly is the argument that explainability is important for fairness. I think that this is a both very important topic, but also something that must not be too easily addressed by something like explainability. What I mean by that is that bias is already part of the clinical landscape. So we know that doctors are humans and humans are biased. Doctors have biases. And so the prejudices that you might imagine exist in humans also show up in clinical care. This has been very robustly established in the clinical and epidemiological literature for a very long time. So we could just audit models for fairness. And we could say, I want to look at different ethnicities, different insurance types, different genders, and I want to see whether I have better or worse prediction accuracies across these different subsets of individuals. But I want to highlight how hard it is to recognize that you might have one of these problems if you're not thinking very carefully. So we took a publicly available word embedding model, Cybert, which is trained not on the internet, but on PubMed articles. So it's trained on scientific text. And we gave it this prompt. So blank race, patient became belligerent and violent, patient sent to blank blank. And these transformer models, these contextual language models, are able to fill in the blank very well. And it's been demonstrated previously that contextual language models that are not trained on clinical text, but that are trained on large amounts of human-generated text online actually have very deep biases. And so here we found that if you ask the Cybert model what happens to a Caucasian or white patient who's become belligerent and violent, they get sent to a hospital. But if you ask the Cybert model what happens to an African-American, or Black patient, those patients are sent to prison. This is really, really disturbing because Cybert is trained on scientific articles. It's publicly available, and it is very commonly used as a contextual language model for generation. So think about our prior example of language generation in X-rays. You would not want this model to generate these kinds of differences. And it's difficult to imagine all the ways that biases present in even scientific documents have crept into contextual language models, and evaluate and audit all of them. So I want to close with a note of positivity. If we want to improve clinical care and practice, maybe there's some things that we can look at. So there's this great article a couple of years ago that talked about how gender concordance increases a patient's probability of heart attack survival. That effect was driven primarily by increased mortality when male physicians treat female patients. And you could argue these burnt out doctors who have little time to be empathetic and are used to dismissing female pain are not listening. And so that's leading to this increase of mortality, specifically in female patients when we have heart attacks. But there's this interesting snippet in the same article that said mortality rates decrease when male physicians practice specifically with more female colleagues or have treated more female patients in the past. So the funny anecdote for that is that women have a great dose response effect. The more you're around them, the less you kill them. But the reality here is that actually there is some improvement when you have more experience, when you have more reference points, when you can draw on more information. And so I think that there's a lot to be said about new opportunities to improve collaboration between models and clinicians, where instead of trying to optimize for a specific goal or metric that was defined maybe with bias in mind, we are trying to improve some sort of end outcome. We're trying to improve the clinician's practice, not some score that they might use in the course of their practice, which might be flawed in and of itself. And so I think that this could be where machine learning actually improves rather than just creating some metric that we then have to say is transparent or explainable. In summary, I think that explanations as a form of transparency are actually really important when we debug our models or when we audit our models. I think that if you're a modeler or a statistician, a developer, you use this daily. You're trying to understand what your model is doing and why there is an error. But it's really unclear how an expert or non-expert end user can or should incorporate explanations or another form of transparency when they use them, especially in a healthcare setting. We know that explanations can cause over-reliance and reduce our audit propensity, and biases that could be created, increased, or propagated need to be attacked with these aggressive audit standards rather than saying, I have an explanation, the model is transparent, therefore you could see if there was an issue, because these are really pernicious biases that could be very deeply embedded, and we could forget or not know how to audit one specific bias. This work was done with a fantastic team of students, collaborations, and fantastic funding sources. And I believe that machine learning for health has a real path forward in creating actionable insights in human health if we focus on making technology that makes humans better rather than making humans better at understanding prepackaged technology. Thank you.
Hi. So hopefully you enjoyed the 3 talks in this session on saving lives with interpretable machine learning methods. Definitely different points of view represented in the talk, so that's a lot of fun. And hopefully you've got some interesting questions for us. We'll start off with a brief discussion, and then we're going to open the floor. Please type in your question, and we'll try to answer it. So let me get started. I just wanted to say that in my own work with interpretable machine learning care, we see at least 4 different uses of the interpretable methods in health. So one of them is, let's take COVID-19, which is happening right now. One of them is the doctors don't know about this disease. It's new, and they want to learn everything they can as quickly as possible about how the disease operates, what the risk factors are, and then what they might be able to do to help treat patients. And they're interested in training interpretable models on new COVID-19 data. And we're interested in doing that, not even so much because we plan to use a predictive model to treat patients. It's because we want to know what the model is learning from the statistics and the data as quickly as possible. One advantage of machine learning is that machine learning can see and digest thousands of patients, possibly patients even coming from multiple hospitals, whereas no one doctor typically will get to see thousands of patients in a short period of time. So there's a hope that the statistical machine learning methods that are interpretable can actually inform us much more quickly about how COVID-19 works. And we're definitely seeing that in our day-to-day work with hospitals on COVID-19. So they're very interested in the models just because they want to learn what they can. Another use of interpretable machine learning in healthcare is actually very different. It's more like that pneumonia asthma story that I gave in my talk, where we've trained a model, we would like to deploy the model and use it, but we want to look at the model and see if everything it learned kind of makes sense or if there's anything risky in there. And for example, we often see that treatment effects, things like asthmatics get to care faster, heart disease patients get to care even faster. They just don't give up on patients over 100 when it's a treatable illness. And if you've got a wheezing in your lung, you're more likely to get to care than if you're not wheezing. Things like that. We see that in the data all the time. And the model learns to predict counterintuitive things, that having asthma and heart disease are good for you if you've got pneumonia, when the doctors are convinced that that is not true. It's the exact opposite. So there, what we want to do is see what the model has learned to basically vet the model and correct the model before we deploy it, and where it might, harm some 100-year-old asthmatics, which we wouldn't want it to do. Then yet a third use of interpretability in healthcare is explanation. That is, we're giving a prediction to practitioners. It could be doctors, nursing, anyone who's treating patients directly. And, most of the time, they don't have time to look at an explanation. They don't really care what the explanation is. If the model is kind of confirming what they already thought, they're reasonably happy to just sort of accept it as, a second opinion. But there are times when they definitely want to know, why are you thinking that this patient is so high risk or so low risk? And they want to see why the model is doing that. And then there's a fourth use, which is the model looks like it's making some mistakes. And that's definitely going to happen when we first deploy models in some new healthcare setting. And you want to debug the model. That is, you want to figure out, why did the model make this specific prediction, which we're pretty sure really is a mistake. So what's going on? So, and yet that's a different use of interpretability, where the data scientists and the healthcare practitioners might be working together to try to debug the model and figure out why in certain settings it looks like it's not as accurate as it should be. So those are very, very different uses, and the kinds of methods in interpretability that you might use for learning from new medical data, COVID-19, might be very different than what you would use for debugging, where a data scientist might be in the loop. Very different from what you would show to an end user, a healthcare practitioner who's actually working with patients. So I thought it would be sort of fun if Ankur and Marzyeh, if they had any comments about their presentations, bias, and whether practitioners should trust or don't trust their models enough, and these sort of different spectrum of, I only want to train a model to learn from my data, to, oh no, I need to actually understand why the model is saying exactly this about this patient. So anyway, I thought I would start the discussion off there, and then we'll open the floor, and hopefully you guys have questions and we didn't answer them all during the chat session.
So I think my biggest concern is with category 3, right? So I think that when users are developing models, we need to debug. We need to understand what's going on. We want to make sure that we're not in an X-ray image focusing on some feature that might be more indicative of the machine that took the X-ray, maybe from a poor hospital that sees more of a particular kind of case, than something that might be reasonable or relevant to the physiology. And I think also when you're trying to investigate in a non-inferential setting, when you're just trying to understand data distributions, whether certain variables are predictive or not, when we're not talking about deploying a model at inference time and listening to those recommendations, I think it does make sense that you want some sort of way to interrogate the model. What I'm really concerned about, and I'd love to hear Ankur talk about actually with respect to bias, is we know that doctors are humans. We know that humans are biased. We know that there are problems, and we don't have good solutions to fix those problems with humans as they stand. But one human doctor is limited by the place that they work, the hours they work, who they can see. But one algorithm could be unlimited in the number of people it touches. And so my concerns are, if we have explanations that we know in non-machine learning settings can anchor your response, that's very dangerous now, because you could convince a whole slew of new doctors that it's fine to mistreat somebody because we have an algorithm with the sheen of objectivity.
Hey, let me make a comment before you start.
Yeah,
I just love Marzyeh's it's the classic, all doctors are human.
Yeah.
All humans are biased. Therefore, all doctors are biased. I just think that's a beautiful and a sad update on a popular expression that dates back centuries. Yeah.
And then you can extend it to one more level of abstraction, and therefore all medicine is biased. Hence, right? Amazing thoughts. And I mean, from my experience over the last 5 years, trying to deploy these systems collaboratively with large sort of cloud scale, right? Getting it done at a cloud scale implementation, and we have been doing this with Microsoft Azure for some time, and large health systems across the world. It is fascinating to kind of rattle off the problems that I have seen, come through. So I'll give you a quick example, a story, right? Downtown Chicago, big hospital, emergency room, Monday morning, 3 exactly same patients waiting to be treated, and amongst 25, 30 patients that are just waiting to be seen. And we were asked to sort of build a model to predict left without being seen. So essentially, the emergency department wants to use some form of machine learning to figure out which patient to triage quickly, who to connect with the doctor, so that they can be taken care of faster and won't just walk away without being seen, because that might be harmful for later treatment, etc., etc. And we trained the model. Everything went great. In retrospective data, everything was fine. Deployed, and boom, 2 weeks down, as we are doing the prospective pilot, thankfully, right, we had sense to not just take the model, put it in the pipeline, and run it in the wild. And following the protocol in the prospective trial, just start seeing that the model is literally, guiding the triage nurse to go and check in with every African American person that walks in, right? And it's surprising because we just hadn't done our work, right? Like we were, and this was several years ago. We didn't know much about the issues that can be there in post deployment processing, and we were learning this thing. And as the metrics started showing, thankfully we have we had built what we call as the model health dashboard internally to start seeing what the class distributions are as the model is making its predictions, and if it conforms to the class distributions of the original class distribution on which the model was trained. And when you start seeing these things side by side, just visually, suddenly the light bulbs start growing. And as we started observing that, we had to literally press a big red button, right? Like the Staples ad saying, stop this model. Let's go back to the drawing board. 2 weeks of data, just 2 weeks of data, and this is happening. And then, of course, we went back to the data, observed, protective classes, ethnicity was a big one, somehow mitigated that, made the thresholds and the cut points at which the model was doing the prediction from a risk score to a binary on who to go and touch, and then adjusted for that and came back, right? That's one example. And I have probably 20 such examples across not just acute care management, but also in diabetes care management and recommendation engines for nudging people for a whole country, and how do you get that going? But simply fascinating, and explanations are, as Marzyeh said, just not enough. It's the actionability. So explanations essentially can be broken down into 3 types: stuff that you can't fix, age, gender. That's not an explanation. Like telling someone that this is happening because of their age is not actionable, right? So there is non-actionable, there is actionable, and then the third framework is modifiable, right? Like what can you modify? So having metrics that look at the quality of explanations across attributes that are non-actionable, actionable, and modifiable really starts helping physicians get to understand how to use those explanations. And then you surface only the modifiable ones at the individual patient level, but you surface the actionable ones at the system or the population level. And then you just, sort of give retrospective idea to the whole sort of leadership team what's happening on the non-actionable one so that population health can do its job. So starting to think about those frameworks in that way really helps when you're trying to deploy these systems.
Hey, there's a question about what clinicians find interpretable and informative that I think is related to what we're talking about now. And most of my work is with clinicians who not only practice medicine, but they're also people who write papers. So let's say they're also research clinicians. So they're statistically more sophisticated, perhaps, than the sort of practicing physician who you might see when you go in for care. And what I find is even with these statistically sophisticated people who write papers, it's critical that a machine learning data scientist person like me is in the room so that we can talk together about how to interpret the explanations. They would not find these explanations 100% informative all by themselves. And even we find it's critical to have a database person in the room who was involved in collecting the data and processing the data before the machine learning ever touched it. And that's because often the bias that we see in the model is actually an artifact of some pre-processing stage or some way the data was collected, earlier. So we saw a COVID-19 bias where it looked like it was good to be older. So actually, the older you were, the healthier it was. And it turned out that the bias was that people who were older were in the hospital longer. We were collecting a data point from every patient every day they were in the hospital. We were only predicting a bad outcome, which is at the very end. So it turns out people who were in the hospital longer had many more days where something bad did not happen. So the older patients actually look like on average they must be healthier, but it's because of an artifact of the way we were sampling data. So I thought you guys might want to talk a little bit too about what you find when you work with your experts, what they find to be interpretable and acceptable.
I have had such an incredibly varied response to this question, which is part of why I don't think explainability is a good idea in deployed clinical models, honestly. I have had panels of clinicians, all from the same background, all with the same level of fantastic training, completely disagree about what they want. And so that's why I put the example at the beginning of my talk of these, these GAN-generated radiology images. And when I saw that, that's Sami Koyeja's work from UIUC. I remember not being able to say anything after I saw that slide, because when he set it up, he said, what happens when you have a good enough example generated by a computer? And of course, I'm saying, well, then the expert can't tell it apart from the real image. No, that's not what happens. It's that some people have preferences for the fake thing and think the fake thing is real. And some people have preferences for the real thing and think the real thing is real. And some people can't tell the difference. I think that amount of variation in what, and this is a consistent field where radiologists are trained to look at one kind of data and make inference about what kind of diseases might actually be present in an image. If we're talking about anything that's more general, right? If we're talking about internists or intensivists, right, who are in an intensive care unit, who have to look at vitals, labs, images, notes, demographics information, I can't imagine a setting in which, there would be a consistent way in which if you asked people, how would you like to see this information? How would you like an explanation? They would agree. But even worse, in the really, traumatizing thing for me in the clinical viz paper was we were visualizing these things for these pieces of data for real doctors. It's real patient data. These are real doctors. We're asking them real questions about what interventions need to be prepped, and using a nice visualization that we developed in collaboration with a clinical team, everybody became much more confident in their choices and not much more accurate in their choices. And so I'm also very concerned about showing people things in a way that makes them feel comfortable and confident and secure, and having them then not audit, which is what was found by Hannah Wallach and Jen Wortman-Vaughan and crew in this New York housing market example.
Yeah, I can build a little bit on that. So in one of the slides, I showed the three dimensions of sort of computational bias, social bias, and cognitive bias. What, Marzyeh, you're describing here, the classic case of cognitive bias. So within that, there is this idea of an automation complacency. And the term complacency sort of originated from references in the aviation community, where accidents or incidents happened when pilots or air traffic controllers or other operators purportedly did not conduct sufficient checks of the system and assumed that all was well, when in fact a very dangerous condition was developing that led to some sort of an accident, right? So technically, the performance consequence could also not involve some omission, but an extremely delayed action. So this type of complacency is what we call as automation complacency. And what it builds is it builds exactly what you described. And there is a whole body of very nice literature that talks about automation bias, where what happens is quite often the decision aids, in our case in healthcare, the visual aid or the risk prediction model, start getting misused for two main reasons. The first is that the automatically generated cues are so silent, not silent, but salient, right? They're so salient that they tend to draw the attention of the user. And secondly, the users themselves have a tendency to ascribe sort of greater power and greater authority to the automated aid rather than other sources of advice or their own sort of training and background. So addressing these two things, sort of automation complacency, and automation bias, and then figuring out which of the two paths this bias is following becomes extremely important in the delivery of the system. So when we look at deployments, we often try to see as we do the user study on the output of the prediction model, if that saliency is actually taking away from providing good quality care into the system.
So I have a follow-up question that I want to ask both of you. And this is in a healthcare setting, when we talk about deployments, often deployments are done under the banner of quality improvement, right? That worries me, because often that positions our research purposefully as not being research. And so the way we think about doing the deployment, the way we think about doing the evaluation, our entire incentive structure is really different. And I went through this recently during a deployment at St. Michael's Hospital here in Toronto, where I kept having to really pull the clinical team back and say, this is still research. We still have to keep our mind in the space where this could be worse. We could not improve things. We need strong baselines. We need to compare to what would happen in the absence of these kinds of interventions or with simpler versions of the interventions. I think there's been several really good papers that have come out recently that have said this is not the norm, right? Often you are told explicitly by the hospital system, well, you can't do this kind of research on patients. That's not ethical. Let's just do some quality improvement. So where does that leave people like us who would like to do this kind of research, but would like it to be, very robust and reliable?
So I know in some of the COVID-19 work that we're doing with hospitals in New York City, they are doing a sort of careful randomized clinical trial rollout of the decision support system. Now they've gone through IRB approval and gotten approval to treat this as an experiment, sort of a medical device, a new treatment. And basically some physicians are getting to see the extra information that comes from the machine learned model, and other physicians are not seeing that. And then they're trying to figure out if, in fact, seeing the predictions from the model actually does help improve care or not. So I agree with you. I think it's very important to treat this as this could just as easily hurt as help, and we need to treat it as research. And I thought what Ankur said was also very important. He pointed out that they did a rollout of something experimentally before they actually rolled the thing out in actual deployment. And I think that's absolutely critical. I've seen cases where something is rolled out experimentally. It turns out it was only trained to make predictions for adults, but accidentally it was allowed to make predictions for children as well in the hospital when it was rolled out. And suddenly the accuracy looked like it was tremendously lower than they expected. And when they looked at it more carefully, they realized, oh, we're letting it make predictions for children. And fortunately, they saw that in a safe rollout before any clinicians had actually seen the prediction. So it's very important, I agree with you, to do these things carefully and treat it as an experiment.
Yeah, absolutely. And the only thing that I would add to that, to build upon, is we in computer science. So just taking the ball a little out of the healthcare field into computer science, right? We also have to think about healthcare more broadly, because when we think of healthcare, we think of patients, we think of doctors, we think of hospitals. That's not necessarily true. Healthcare and wellness is a much broader spectrum. So there is, while we can say quality improvement for something in the hospital setting, there's a lot of stuff happening in devices. There's a lot of stuff happening on wearables. There's a lot of stuff happening in personal health that people are in charge of in terms of taking care of predictions and outputs. So how do we figure out a way to address fairness as well as address explainability in those settings is also very interesting. And I've been looking at some of that, but think a little broader is my advice to the computer science community.
I worry.
I hate to do this, but we're well over time, so we are going to have to wrap up. Thank you very much for watching. Thank you for the great presentations. And we are happy to chat with anyone who wants to get in touch with us afterwards. I mean, we really like doing this. So we would be very interested in talking with people who have further questions. Please reach out and contact us. Thank you again.
Thanks.